Hi everyone, I'm Yoshihiro Nakajima from MTT. So I'd like to talk about our project to enable the SDN for high performance switching using the DPDK libraries. Okay, so today's agenda is here, and we like to talk about the motivation and what is our project called Lagopus. And also, we would like to share some speed improvement and optimization using the FPGA Smart NIC. Also, we share some experiments in the last big event in Japan. Okay, let's move to the our motivation for fun. Okay, so we are in the big changing point from legacy to future networking. For example, the legacy system usually the hardware, special hardware-based, and it is difficult to extend some capability or functionality for our demand. So now, we prefer the open source and general purpose servers and CPU. Also, we have a lot of tools to enable the flexible networking. And that's why we develop our control plane and the switch system using the SDN technology and the DPDK. So, okay, so let's move to our introduction of Lagopus SDN switch project. So this is basically, so we try to provide an NFP or SDN aware switch framework that includes the SDN switch agent, high performance data planes. Also, we also provide flexible extensible switch configuration database. And we have a lot of extension for DPDK to enable the flexible configurations, also the high performance virtual NIC, and extension for a DPDK aware NIC system. And so another goal of our project is to expand the software-based packet processing to carrier system. So basically, the carrier tried to leverage the hardware appliances due to the performance issues or scalability issues. So our challenge is to bring the software data plane using the general purpose servers to production network. And so in our target, basically our project can be applied to many switch system and gateway system and hypervisor switch system. And also we try to enable the high performance software data plane. So which is SDN aware and also much capacity support. For example, in our use cases of a carrier system, sometimes we need 1 megaflow capability. So because we have to manage the many route and policies and ACL and so on. And another point is that high performance in case of the short packet. So usually the server system is designed for the large packet size. For example, the file transfer or data communications. But in case of a network system, so we have to support the very small packet handling in very high speed rate. And Also, in our career, so we have a lot of support for frame format, such as MPLS and PBB, Mac in Mac, IPv4, IPv6, and also, many people said so pure SDN approach does not work. So we try to support a hybrid SDN. So that means we can allow the distributed autonomous protocol network control, such as ARP, BGP, OSPF, and so on. And in some use cases, for example, the traffic management and failure handling, so we want to control the whole of network using some API or management softwares. And another topic is the high performance virtual switches for NFV or cloud system. The problem of the current NFV system is so we have a lot of bottleneck in hypervisor switches. For example, so some network I/O causes a lot of VM transition in case of the CPU handling. That's why we try to decrease the portion of overhead caused by VM network I/O. Okay, so I'd like to introduce our Lagopus vSwitch architectures. So this is yet another virtual switch. So the system itself is from the scratch. So no reference with other competitors. Because we have a lot of issue in performance and management aspect. So that's why we have started a new project to develop the high performance virtual switches. Basically, so we refer the reference model of the switch system. We provide a lot of components to enable the SDN switch and control. We have developed the switch agent, switch configuration database, and management APIs, and we have committed to DPDK extension, such as virtual NIC and dynamic port attach and detach extensions. Also, for the more performance, we have developed the software dataplane aware FPGA NIC. So I will show you later. Okay, so I'd like to talk about the fun with the speed. For example, the optimization for the speed using our novel packet handling technique, also the Smart FPGA NIC. Okay, so this is basic packet processing. Maybe you know the first packet comes into the servers. The server handles the network I/O receive, and also then the server tries to parse the frame for the post-processing. And next, the software data plane tries to perform the flow lookup and actions. So that includes a lookup and header rewrite and encap, decap for the toners. And then we have to do a QoS or queue management system. And finally, the system sends the packet to the outside of the servers. So this is a basic packet processing. So what we did for the performance, so we have a lot of techniques here. for example, in the network I/O, so we use the smart flow classification for the multi-core area. Also, we have a lot of technique to gain the performances, such as delayed frame evaluation, the parallel flow lookup tree compaction, and novel lookup algorithm for the OpenFlow system. That is master aware, mask aware, priority aware. It's a lot of things to do. And so we, sorry. Maybe I sent it wrong. Okay.
So in your previous slide,
okay.
Are all these pieces in software, or is there an FPGA support for any of them?
That's a good question. Basically, our approach is software based, but so we need a kind of off-road system, such as queue management system or policing, so that consume a lot of CPU cycles. So we want to offload such kind of processing to the hardwares. But we know that there are a lot of limitations for the hardwares. So we think that it is better to enable the hybrid optimization using the merit over CPU and the hardware system. Okay, I'm sorry. So the slide itself is a previous slide. I showed here we we try to want to see show you our progress for the performance improvement. So the project itself has started from since 2013, and the first year. So we so before the project, we measured DPDK I/O performance. So that DPDK did a great job. So for example, so we achieved the 10 wire rate in case of the short packet, only for the packet I/O. But we still need to think about the high performance lookup and action for the SDN-aware switches. For example, we started our project using the OpenFlow technique, but so maybe you know the lookup for the OpenFlow is quite a lot of CPU cycle. So that is a very tough thing to do for the wire rate in case of the server system and the general purpose NIC. So, from the 2000, the fourth quarter of the 2013, so we could achieve the 10 wire rate using the many high performance technique that described in the previous slide. Okay, so before this project, so everyone said so software data plane is nonsense because no performance and no capability for the carrier system. But now, so we see many people are interested in the software data plane using the DPDK. So because the performance itself is very good, I think it's great. So maybe you can do a think wireless using your laptop or your desktop system. So also, so some my colleagues said, so they want to exploit the software data plane for their own use cases. I think the big change happened. And next, so we'd like to share the Smart FPGA NIC activity for the DPDK software data planes. So, you know, the basic performance of DPDK depend on the CPU performance. But we think network I/O is not optimized for the multi-core CPUs. For example, so the general purpose, so current existing NIC system provide the RSS receive size scaling for the data center protocol such as VLAN, IPv6. But so in our use cases, so we have to support the other, so one aware protocols such as MPLS, PBB, and so in our use cases, the general purpose NIC, it does not provide such kind of RSS. So that means that we cannot leverage the hardware offload. And also, so we think software-based processing are very heavy in some cases. So with packet classification, also the packet dispatcher are very heavy. So only using the CPU cores. And so QoS and policing needs a lot of CPU cycle. So that's why we want to offload such kind of processing to the hardware. So, so in summary, we can see some bottleneck in the receiver side and lookup side and the QoS side. So we try to leverage the co-design of a NIC and a software data plane for performances. So as I mentioned before, so we use the hardware offload processing of FPGA prototype NIC to enable the flexible hardware-based packet classification and dispatching. And we enhanced the hardware-based packet marking for the post-processing. So that allows the sometimes reduce the size of lookup tree. So that means we can perform the flow lookup compaction. And also using the smart, flexible, controllable hardware-based packet classification, so we can leverage the multi-core CPU powers for the many threads. So what we did in FPGA NIC, we extend two portions of components of a NIC system. First one is a smart classification, and the second one is a dispatcher to the many hardware queues. So that allows the, so in case of the high performance, maybe for example the 40 gig, so the I/O thread cannot retrieve the many packets to the user space. So we can divide some flow to the several hardware queues, and we can increase the number of I/O threads to retrieve the packet. Also, using to enable the flexible control to the flow classification, so we can do load balancing for the many queues. So this is the ideal case of the packet classification and packet dispatching to the physical queues. And also, so we extend the front-end hardware-based packet classification and packet dispatcher for the post-processing. So I mean, so basically the flow lookup needs a frame match or a longest break match and exact match or mask match. But so we can leverage some hardware offload that mark the using the simple lookup based on the hardware offload. So if we do some VLAN or tag match and IP lookup, so we can offload the very simple lookup such as a VLAN or MAC addresses lookup to the hardwares. So that allows the very simple compaction of the flow lookup in the software data planes. And also we extend our FPGA NIC to enable the DPDK flow director API compatible to allows the easy to port to the other system. So this is our preliminary performances. So we can see our proposed method can achieve the 40 gig wire speed from the more than 38 bytes packet size. So compared to the same cores, so the yellow line and the green line, in the same cores, we achieve the maybe 50% higher than the existing way to enable the high performance. So that means so we can achieve the high performance as well as we can decrease the number of CPU cores to achieve the same performance. So that is a good for the software data plane because in some use cases, for example, the tunnel handling or very microflow control to the some of our use cases. So we need much core for the complex flow lookup. So in this small extension of the Smart NIC give a great benefit for the software data planes from the performance improvement and as well as we can save the CPU cycle for important processing in software data plane, and we can save the CPU cores for the same processing with the standard NIC. Okay, let's move to the our fun with experiments in last our real use cases for the SDN-IX. So in last May, we have a big event, internet big event in Tokyo, so called Interop Tokyo. Maybe in the United States, the Interop is not so popular now, but in Tokyo, so maybe one 100,000 people joined to this conference. So this is a big event. And so this work is done with collaboration with Nekoma project, so which is a NICE and University of Tokyo joint project. And so before the introduction of SDN-IX, so I would like to share what is a IX. So maybe, so here, there are many network guys, so you know what is IX. So IX is basically internet exchange for service providers. In the IX packet exchange point between the ISP and the data centers and the service providers, and the service provider prepares the border router to exchange the route information for the internet. And so there are a lot of issues to the next generation of IX. So one is automation. So basically, the current IX just so accepts the service order from the ISP. So that means manual operation are required. And also, recently, we are suffering from the huge DDoS attack from some countries. ISP want to reduce the DDoS-related traffic in the origin side. And sometimes DDoS attack traffic occupies a link bandwidth up to the 100 gig or, yeah, it's too huge traffic exists. And so for the such issues, so we extend the IX capability for the next generations. So the SDN-IX is basically provide inter-AS layer 2 connectivity between the border routers. And also we provide a kind of network protection mechanism from DDoS. So in this POC system, we just provide a 5-tuple-based packet filtering. And to enable the SDN-IX, we set up the SDN-IX controller and distributed OpenFlow IX core switches. So this is a venue network in the Interop Tokyo. So we installed the 2 Lagopus software switch in the IX system, connecting the 10 links with several ISPs. And so in this demonstration, we use the Ivy Bridge core E5 8-core CPUs. And here, so this is our Lagopus switch. And so there are 2 optical transport systems connected to here. Okay, so this is an overview of path provisioning between some service providers. So each service provider requests to the IX controller to open the path between some ISPs. So the system automatically provisions the path between some ISP using the layer 2 technologies. Also, we measure the traffic in the one interfaces of Lagopus software data plane. So we measure the in average 2 Gbps throughput, and no packet drop, and no reboot, and no trouble for the 1 week. So this is a conference sessions. And sometimes so we measured the 10 wire rate. Maybe some tester, some operator performed the 10 tester in the venue network. And also, this is a very fun to see the big change from the before the Interop Tokyo and after the Interop Tokyo. So before the Interop Tokyo, so many network operators said, so vSwitch has a lot of issues on performance, scalability, blah, blah, blah. A lot of things complain to the vSwitch. But after the Interop, so they very happy to use a software data plane for some use cases. Good performance and good scalability and stability. Yeah, it's a very fun for me. Okay, I'd like to summarize our talk. So, our project tried to commit to the high performance vSwitch development for fun. So I think the performance optimization and the improvement is very fun. Yeah, and we try to extend some component to get much performances in NIC system, DPDK, and other internal mechanisms. Also, so let's try to changing the everyone's mind using the DPDK and the software data plane for fun. Oh, sorry. So this is a previous slide, previous version of the my talk. So in the IDF, so we have demonstration in booth number, I think 173. So please visit our booth to see Lagopus vSwitch. So we have 2 demonstrations for performance benchmark and some use cases for wide array carrier use cases. Thank you. Okay. Okay.
Are you planning to sell your switch as a product or some open source?
Yes, our project is open source, and you can use your own purpose, and you can, yeah, do.
The code for the FPGA is available too?
Not yet. So because some IP regulation, yeah, it's difficult to distribute the source code. Okay.
Do you expect people to actually deploy FPGAs in carrier-grade environments, or are you hoping that NIC providers will take the mechanisms you put into the FPGA and implement them in their NICs?
Yeah, I think the existing some network node leverage the FPGA for some processing, maybe the protocol handling was path changeover or something. But so in this project, so we just show the merit of a prototype of FPGA for data planes. So maybe I hope that some vendor try to use the same idea for their own product, and we are very happy to leverage such brand new NIC for the data planes for the fun or speed up. Okay.
Does the FPGA NIC support SROV, and have you tried to ask the NIC providers to add such hardware features for you have implemented in your FPGA?
So it depends on the use cases for the data plane. So that means in case of the data center networking, so the current capability and functionality is enough for some use cases. But for the next step, for example, some user want to leverage the MPLS technology in data center networking, but the current existing NIC does not support such kind of
I mean, maybe some NIC providers can provide the feature in the future. It's easier for you and others, right? And, I mean, maybe you don't need to do that FPGA in the future.
Yes, if the NIC provides FPGA, same capability of our what we did in the FPGA NIC, so that's enough. But so we try to find some bottleneck in the our use cases. For example, the accuracy of the packet policing and QoS is not enough by only software data planes. Sometimes the software data plane causes burst traffic for the to the other network.
So did you try with the 1 gig, 2 meg, huge page? Do you have any feedback whether 1 gig is better or 2 meg is better? Huge page size?
Yeah. So the last experiments, we enabled the 1 gig huge page, and we enabled the jump packet. But we think for the to allow the mix of the jump packet and the small packet, so we have to prepare the huge amount of memory size in the system, DPDK system. So we think sometimes that causes a lot of cache miss or memory swap out. So that's caused a lot of performance degradation, and that's why we have to care about the page size and other similar things. Okay.
I have a question about the Lagopus.
Yeah. Yes.
Did you start that? Is that a complete separate source base, or is it forked from OpenVSwitch?
Okay. So your question is why we conduct the brand new project to we think OpenVSwitch did a great job for the data center networking, but in our use cases we need a kind of another support for the SDN. So that's why we started a brand new project. So for example, in case of the data centers, the number of routes is limited, and the protocol also limited. But in our use cases, in the carrier system, we have to support the many route informations and stability in case of the burst route injection. So we try to provide a very high performance and stable software switch for carrier use cases.
Okay, and I noticed you also added MPLS and DVD, which are sort of there in OpenVSwitch, but is the source, is that completely open source and is it available?
Yes. Please, find our project name Lagopus in the GitHub page. Yeah.
Thank you very much.
Okay.
What did you do for DDoS? I mean, you mentioned that it helps, but
Okay. So the current SDN-IX controller doesn't provide a smart way to protect the DDoS attack. So, for example, the IAT people propose the flow spec to accept some request from preventing the DDoS attack from the ISP. So we think so. The current system only accept some request of the packet drop in some network mask format. So for example, so if you want to reject the 20.0.0 slash class C or class B, so we just install the drop rule to the switch system. Then the switch usually through the packet to the destination, but if I met the IP packet in the given IP addresses, so we just drop to protect the system.
How the VM connect to your vSwitch? What kind of driver you need to connect to your vSwitch?
So our system can accept the DPDK enabled virtual NIC framework, such as a BAT.io and vHost user or other similar way.
So you support vHost user?
Yes. So detailed information, you can get some instruction to install our good way to enable the virtual NIC for KVM system on GitHub site.